So thanks for the invitation to come here. I figured that since most people in the audience may not have much of a background in general relativity, that I would try to sort of give more of a kind of survey of what kinds of questions that this approach can answer. And so I'll sort of flash a lot of ideas and results that I think are important, but this will be completely superficial. Everything that I'm going to talk about today, I think, can be found in this book that I wrote with Subir Sachdev and Sean Hartnell, but you can get it for free on archive if you want. It was a review article that was 3.5 times over the page limit, so it became a book. Anyway, I should start by defining what this thing is that we're going to talk about. So ADS-CMT is a pun on the anti-de Sitter conformal field theory correspondence, which may also go by the name of holography or gauge gravity duality. Let me focus on this lattermost term. So the gauge theory, in the classic canonical example that I'll just show to give you a flavor, this would be the 4D maximally supersymmetric Yang-Mills theory. So we have SUN gauge field with a non-abelian flux. I forgot to write the second term. We have a matrix-valued bosonic field phi and a fermionic partner. This is some nonlinear action, and there will, in general, be n by n matrices. We'll typically imagine n is large. And there's also a coupling constant lambda that I won't say what it means. This is one side of the duality, okay? And this theory can be thought of as the effective theory that lives on stacks of d-branes in string theory.
And also fermions, right?
There are fermions, but they're fixed by supersymmetry. Yes. I didn't write, I mean, this is all in the ellipsis, but they're there, yes. Okay. The conjecture is that this gauge theory is in a certain limit dual to a much simpler gravitational description on ADS5 cross S5. Now, we generally ignore this internal space, especially for what we'll be talking about today. And so, in some sense, we'll think about this as a duality between these kinds of matrix large N models and a theory of gravity. Now, historically, this duality was really, I think, most exciting because it served as a tentative definition of quantum gravity, which we don't really know how to carefully define. We won't be using it for that purpose in these lectures, but this is, in principle, a quantum theory of gravity. We won't study it in that limit. Okay. The limit that we'll be focused on in these lectures is the limit where the matrices have a large number of degrees of freedom. So they're big n by n matrices where n is much larger than 1. And we'll also take this coupling constant lambda to be very. This regime, this gauge theory is strongly coupled, okay? And although there is a sort of diagrammatic expansion for this theory, you don't get away with some one-loop calculation and that's it, okay? If you wanted to consistently treat this system when lambda is large, you would need to sum an infinite family of Feynman diagrams, and that's not fun, okay? So the idea with this duality is that we can think of this gauge theory in this strongly coupled and very intractable regime through sort of ordinary diagrammatic expansions. The idea is that we can think about this theory as instead via a dual description. The simplicity of the dual description is that the gravitational theory will be approximately classical. The Newton's gravitational coupling constant Gn, you can think of Newton's force law G, m1, m2 over r. It's the same thing. This gravitational coupling constant will be 1 over n squared. Okay? And so it will be a perturbatively small parameter. And in the dual description, we will have a semi-classical saddle point to work with. Okay? Yeah.
In the first theory, the action grows linearly with n, is extensive in n, but in the second picture, it grows quadratically with n squared. How do you reconcile those two facts?
So I think I think with this normalization, the trace gives you 1 extra power of n.
I see, there's a hidden SUN or something inside the trace.
Well, it's a trace over n by n matrices, so trace of the identity would be n. Yeah.
Also, in the second theory, does the dot 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 contain the fermions?
So the dot 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 contains essentially corrections that are related to 1 over lambda that are higher derivative gravity. In principle, there could be fermions in the bulk. There's actually a bit of a debate about this. Because the question is, as we'll see, a fermion in the bulk theory would correspond to some sort of interesting single trace fermionic operator in the boundary theory. And those may not be relevant.
Is there a chiral anomaly in supersymmetric granules?
If there is, you can easily include it in this gravitational theory, but I don't recall off the top of my head. I think there is, and it can be accounted for. Yeah.
You also mentioned string theory of Branes, right? So what kind of string theory type?
This is type 2b string theory on the D3 branes.
Which is chiral, right? This is deep.
Yeah, but this is a highly supersymmetric version. I don't think this is a chiral theory. But anyway, yeah, I don't remember that detail. Anyway, there's no proof of this duality, but there's a lot of evidence for this duality. I'll show some of the sort of evidence, at least heuristically, for why we believe this duality is true. But there's also some sort of systematic checks that you can do on this side and this side in various string theoretic versions. Yeah?
Maybe I can ask an intuitive question. So I actually read the book, and your book. But basically, the idea is the D branes, right, in 2 different limits. In one limit behaves like a gauge theory, and the other limit behaves like a classical black hole.
Yes.
Right. But why don't we just say there's a phase transition between these two? Why do we?
Well, okay. So the logic, I would say, is basically that it's really that when lambda is very small, that this writing down this action is a sensible treatment of the theory, in that we can use our sort of conventional diagrammatic expansions on this action,
Right.
and this gives
But
a
why do we
controlled
still
description.
believe this action is still correct for the other limit?
Well, a sort of heuristic argument is that if you imagine this stack of branes, when lambda is large, they basically become very strongly self-gravitating. And then you could imagine semi-classically solving, let's say the equations of supergravity for, at least in some semi-classical approximation, what these branes would do. And they end up forming a sort of black hole with this near-horizon geometry. And so that's at least some intuitive evidence for why this should be true. But it is ultimately a conjecture, so I don't want to go overboard. Okay.
Are you keeping a ratio of n over lambda finite?
No. No. These can be separate. You can take these limits separately.
So which ones will we be taking?
Typically, one wants to take the large n limit first, because corrections in 1 over lambda are adding sort of more terms to this semi-classical action. Corrections in n are essentially quantum gravity, because it's loop corrections in Gn. So those are sort of more annoying. Depending on the parameters that you hold fixed, though, you could imagine that lambda is kind of like square root n in this system. So it is strictly true that n goes to infinity first, but n over lambda squared may be finite. All right, anyway, I mean, I don't want to spend too much time on this. I just want to stress that there is some sort of historical origin to this duality coming from high-energy physics. Now, the relevance of this duality for condensed matter theory, these are the motivations that I would give for why condensed matter theorists should pay some attention to what we're doing here. So first and foremost, this gives us a description of quantum matter without quasi-particle excitations. And in a number of contexts, I would say it's fair to say that for various phases of quantum matter that we have, I don't know of any other tractable description of non-quasi-particle matter. So this is a very useful tool to have, even if it's maybe a little artificial in a sense. Another useful feature of this duality that I will touch on at the end of the first lecture, but probably will not give enough justification to, is that in many ways you can think of ADS-CFT as sort of a geometric encoding of the entanglement of the many-body system that you're studying. Okay? So this, in some sense, tells us what this bulk geometry actually means. Okay? It's not some totally artificial construct, but it does sort of directly in the many-body context encode some physical information. As a practical matter, there are a number of questions that are sort of painful in conventional condensed matter field theories, like dealing with real-time dynamics at finite temperature, finite density, or adding disorder, particularly adding strong disorder. Many of these questions are more or less intractable using conventional field theoretic methods, but in holography, they're quite straightforward. Okay? And similarly to I think something I just said, it's very easy to do real-time dynamics, especially far from equilibrium. Okay? All right. Now, the sort of classical complaint about working on this field is that this large n limit isn't realistic, and the real world doesn't have n by n matrices. I think I've heard that a number of times. In response, I would say that, not all theorists, but a large number of condensed matter theorists already have lost touch with reality, so to speak. So there are vector large n expansions, right, for the ON model. We do 3 minus epsilon expansions when we want to study critical phenomena in Wilson's RG. We do all-to-all interactions in models of spin glasses, and more recently in the SYK model. So there's all sorts of models that we've used over the decades that are sort of useful because we can do them on a pen and paper. Okay? And the point is that holography should be taken with the same grains of salt as you would take any of these other models that I've just mentioned. Yes?
Sorry, this is a very basic question. So n, is it the number of particles in the system, or is it the number of...
I mean, you can think of it as roughly the number of degrees of freedom in the system. So you have these n by n matrices, and each element of this matrix you can think of as like a creation or annihilation operator for a harmonic oscillator. And then there would be one of these at every point in space. So there's n squared degrees of freedom.
But Andy, in defense of those other expansions, in those cases we're doing an expansion around a Hamiltonian or a field theory that we do know about. Whereas here you're building this on a conjecture on a conjecture.
Yes, I mean, this is maybe the most egregious example of this, but I'm just commenting that what I would say is that, these models, as I wrote here, don't take cartoons too seriously, okay? This is meant to be a useful toy model for phenomena that are very difficult to compute otherwise. So if, for example, you imagine you have some soup of a quantum critical non-Fermi liquid and you hit it, with a lot of energy, and you ask what happens as a function of time, it's very difficult to do this calculation, if you start with a microscopic Hamiltonian and try to put it on a computer, or even worse, do this by hand. So this is a sort of extreme cartoon, but it's an extreme cartoon that allows us to look at some extreme problems that we can't address otherwise. Yes, if the conjecture is true. At the very least, this conjecture has never given, I would say, sort of manifestly incorrect answers. They're always self-consistent.
That's why it's a conjecture on a conjecture, because the first conjecture is about what you just mentioned, gauge gravity duality, and that seems to be in reasonably good shape. But the second stage is conjecturing that we have a much broader class of theories, well beyond the gauge gravity dual, which also express this,
okay.
this duality. That's a conjecture on a conjecture.
So let me make one comment here. So it is true that in much of the literature, people just sort of make up a bulk action that seems useful, and then they study it. But there are a number of results that I'll talk about that come from models whose string theory duals we know. Okay? So for example, in the next lecture, I'll talk about disordered ABJM theory, which is the theory of M2 branes in string theory. So this is something where, in principle, we do know exactly what the microscopic system we're talking about is.
Along the same line, sorry, to give you on this slide. So we know in condensed matter the number of spatial dimensionalities does matter. One is very much different from two, and two may be different from three. So in this regard, how serious should I take the 10-dimensional manifold for young Mills as a
Well, so okay, in practice, we only need one extra dimension. The other internal dimensions, their role is basically that they support higher form fields that essentially stabilize this geometry in supergravity. But from a practical perspective, they're not playing a role in the dynamics. You're not exciting excitations that fluctuate on these internal spaces. So it is true that certain aspects of holography change depending on the dimensions that you're looking at. It's not terribly unlike condensed matter system. I'll come back to that point a little bit later. Okay, and the last point I would make is just that effective theory tells us that sometimes not having a microscopic Hamiltonian can be liberating. Okay, because we don't get caught up on sort of microscopic details. Okay, this is again sort of taking all of these arguments to a very extreme limit, but. Yes?
So I just wanted to ask, maybe we'll talk about this later, but so GR is Lorentz invariant, like if you have Lorentz invariance over there and you have certain metrics and all that, but...
I'll come to this point later.
Okay.
Yeah. Okay, so let me... What? Yeah?
You mentioned about symmetry case theory.
Mm-hmm.
Then symmetry is necessary for this CMT.
So in the approaches, in what we would call bottom-up models, these are always supersymmetric just because we don't really know whether non-supersymmetric string theory makes sense. There's actually some debates about this in the literature as of at least 2 years ago, and I'm not sure if they've been resolved. Again, we won't really see supersymmetry show up in the results that we're interested in. So I would say, as far as we can tell, it's kind of some hidden ingredient in this sort of mystery boundary theory that we're not ultimately going to be that interested in. Okay. Now, the conventional approach, and of course this is not the only thing that we do in CMT, but a sort of very common approach that we take, and just when doing field theory more generally, is we start from a solvable model, which is often free, or in some sort of secret sense free, and then we weakly perturb around that solvable special fixed point. Okay? Now, for example, the vector large N expansions in the ON model and the small epsilon expansions both fit into this framework. Okay? This coupling constant G will effectively follow this perturbative parameter. Now, usually when you do this, as long as you're not crossing a phase transition, properties like thermodynamics are pretty benign. Okay? So let's say if we start with an average energy density at finite temperature, which scales as T cubed in our Yang-Mills theory, or T to the fourth, sorry, when we turn on a coupling constant, we'll get some other correction that scales as T to the fourth. Not very exciting. Okay? But the dynamics is quite singular, usually. Okay? So for example, if we take this sort of a system which has long-lived quasi-particles, and we calculate response functions, like a conductivity, we often get essentially very singular structures, Drude peaks in the conductivity, and these Drude peaks are coming from the fact that the operators that we're studying overlap with these almost conserved quantities, quasi-particles. Okay? And these kinds of Drude peaks will be very unphysical when we take a strong coupling limit. There is no sharp peak that will be left. And so it's very suspicious to take a formula like this that is really capturing some physical structure in the small coupling limit and then just sort of blow that coupling up to 1 and trust this Green's function. Okay, that's sort of, I would argue, more nonsensical than just jumping to ADS-CMT, where we'll get a manifestly sensible formula, albeit in a theory that we don't know the Hamiltonian for. Okay. And there's an example of this in large N vector models in this old paper. Okay, so the framework of holography roughly goes like this. So we want to organize our description of the dynamics around the desired observables that we're interested in instead of quasi-particles. So if we're interested in, for example, calculating the electrical conductivity, we would calculate some effective theory, if you will, some holographic effective description that essentially only gives us the dynamics of the charge current operator. So there's no quasi-particles, there's no large N matrix degrees of freedom that we're calculating or we're dealing with in our calculation. The calculation will only give us the correlation functions of this current operator. Okay? So it sort of zooms in on a theory of only the operators that we're interested in measuring. One thing which I'd like to point out that I'll focus more on in the next lecture is that out of these kinds of emergent theories, there will be a number of kind of generic features that these systems all have, and one of them will be dynamics on this Planckian timescale, h bar over kt. And dynamics on this timescale has showed up in a number of strongly coupled systems in both nuclear physics and in condensed matter physics. And so this is sort of one reason to think that at least some aspects of what we're calculating in holography are reasonable. Okay? So this lecture, I'll talk a bit about, at least sketch out how we do holography, talk a little bit about what kinds of phases we can realize. This is really not new condensed matter physics. It's just to give you a sense of how holography goes. Okay? And then in the afternoon, I'll talk about dynamics, transport coefficients, viscosity, diffusion, conductivity, and far from equilibrium response. And this will have, I would say, more new physics. And these are topics where holography has kind of added to the conversation in condensed matter. Okay.
So do we know results for, let's say, for the emission spectrum, because you're focusing on 2-point correlation functions?
Holography is a huge field. So there's been a lot of work on, for example, fermion spectral functions. I just don't have time to cover all of these things. But you can read the book if you want references. Yeah. Okay. So, so the conjecture of holographic duality is formally stated as follows. This is a paper from Witten. There was another one by Gubser, Klebanov, and Polyakov, but this one is probably easier to read, as is usually the case when Witten writes something. The conjecture is as follows. The partition function of quantum gravity expanded around a negatively curved space. This negative curvature implies that this partition function has boundary conditions on the boundary of space-time. This partition function of quantum gravity is equivalent to the generating function of correlation functions in a field theory where the boundary conditions become the sources of the operators in the dual theory. Okay? So in a picture, you can say, I have this gravity theory in the bulk, which we'll see as semi-classical in our large N limit. And it's dual to a quantum soup on the boundary that doesn't have any quasi-particles. Okay? And so for our purposes, this side of the duality is hard to compute from first principles, but this side is easy. Okay? All right. So I've already said the left-hand side is the generator for correlators in the field theory. The right-hand side is this mysterious object, the partition function of quantum gravity. Really, the only thing that I want you to take away from quantum gravity is that one of these fluctuating fields will be the metric. That's what it means to be a theory of quantum gravity. Okay. We'll explain why shortly. Okay, I already mentioned the boundary conditions coming from negative curvature. We'll mention in a moment. When this theory, on the left-hand side, is the theory of large N matrices at strong 't-Hooft coupling. That's the lambda from the first slide. This object is difficult to compute, but the gravitational coupling constant is 1 over n squared. This is a perturbatively small number. And so we can estimate the quantum gravity partition function in the saddle point approximation. Okay? And if we want to talk about field theories at finite density, finite temperature, in disordered backgrounds, okay, all of these kinds of questions, basically what this will amount to is either adjusting boundary conditions or sources on ZQG, and this will allow us to study, the system as a function of coupling constants and temperature and so on, all from the same bulk gravitational theory. Okay?
Have we established that the mu's and nu's go from 0 to 3 or something like that yet, or are we to talk about
Mu's and
like the indices? Is it a four-dimensional?
oh, this is a sorry. I should have used other labels. This is in the ADS5 to Super Yang-Mills story. This would be a 5x5 symmetric tensor. Okay. Yeah. So one of the indices here doesn't include the bulk dimension. Okay. All right. So schematically, as we saw in our dictionary, for every bulk field that we have in our partition function, there should be some corresponding boundary field. Okay. And the form of these boundary fields will typically be what we might call like single trace operators. So there'll be traces over large n matrix degrees of freedom. Okay? Now, roughly speaking, the way that this works is that for every operator of dimension delta that you have in your theory, okay, in your field theory, there will be a corresponding bulk scalar field in the gravitational description whose mass will be related to the dimension of the operator. Okay? I won't try to justify this, but this is just sort of a classic result from this field. Okay? So this is a sort of example of a common trope that tuning something sort of mild in your bulk description changes something more dramatically in the boundary theory. Okay? So here, just adjusting the mass is changing the scaling dimension of your theory. It's changing the theory that you're looking at. And m squared can be negative. We'll see that a little later on. Okay, if we have, let's say, a conserved global current in our boundary theory, like the charge current that we want to compute two-point functions of later on, that charge current will be dual to a bulk gauge field. Okay? The reason for this is as follows. So anytime we have a conserved current operator, it obeys this Ward identity. Okay? This is really an operator statement. So d mu j mu equals 0. If we go back to our generating function, right, if d mu j mu equals 0, that means that we should be able to freely shift its source a mu by a gradient. Okay? So this is very suggestive that in the bulk description, we'll have a gauge field that's dual to j. Okay? And the gauge invariance in the bulk will encode the conservation law in the boundary theory. Okay? Now we can understand why we're always talking about a gravity theory when we have these holographic descriptions. The reason is that every sensible field theory that we can think of will have some stress tensor. Okay? So there's an energy, a momentum, and currents of these objects. And the stress tensor T mu nu in a general field theory couples to gravity. Okay? So if you want to perturb, if you want to calculate correlators of T mu nu, you do that by coupling your system to a fluctuating classical metric. Okay? In the context of holography, that fluctuating metric becomes a truly dynamical quantum metric. Okay? All right. A little bit more about symmetries. So any sort of global symmetry of your field theory, like translations, rotations, and so on, that leave correlation functions invariant, okay? Obviously, if they're leaving this correlation function invariant, and we believe this holographic dictionary, then whatever transformation this is doing must also leave the partition function of quantum gravity invariant. Okay? And so this allows us to, at least at the semi-classical level, essentially figure out what kinds of geometries we should be studying if we're interested in field theories with various symmetries. Okay? So for example, if we're interested in a system that has conformal symmetry, which is basically scale invariance plus Lorentz invariance plus extra, which we call special conformal transforms. Okay? This is this symmetry group. And there's really only one space-time that's this symmetric, and it turns out to be anti-de Sitter space. Okay? So this metric corresponds to ADS space. And this metric, we would say, has the same isometry group as the conformal group. If you will, transformations of these coordinates that leave the metric invariant are conformal transformations at the boundary, and thus on our boundary theory. Okay. So the symmetry of this field theory is manifested directly in the symmetries of our metric. Okay.
Sorry, so if the boundary has a very high symmetry like the Virasoro, so what is it?
So for the Virasoro case, this corresponds to ADS3, which is, I mean, in that case, I would say there are debates about whether, let's say, pure Einstein gravity in ADS3 is actually dual to a CFT, but roughly speaking, we believe that that's how the duality goes. I don't have a great answer, but there are sort of, I think, dynamics in 3 dimensions is extremely constrained. There's a sense in which the only dynamical degrees of freedom live on the boundary. I think this extra constraint is roughly in correspondence with the enlargement of the conformal group in 2D.
Another question. So for example, in all the way from liquid theory, in the infrared limit, there are a lot of conserved quantities with particle number at every pattern from surface electric conserved.
Mm-hmm.
So I don't know. I mean, so should that be viewed as a part of symmetry? So should it be viewed to our theory about?
I mean, let me sort of answer this with an analogy. So if instead of Fermi liquid, I just take a strictly free theory, okay, which has even exactly conserved quantities, that is conjectured to have a holographic dual called Vasiliev gravity, and we don't know. We know how to write down semi-classical equations of motion for Vasiliev gravity, and that's it. Presumably, its quantization is through understanding holography better. But that's sort of it's nasty. It's a very complicated story. This is probably a good example of what not to use holography for. Okay. So this approach will only be useful when the bulk theory is simpler than the one you started with, when it has a small number of fields.
Yeah, the main message is if the boundary is simple, the bulk will be nasty and complicated.
Yes, exactly.
If the boundary is complicated, the bulk can be simple.
Yes. I think John McGreevy calls this conservation of evil. I mean, you're never going to get lucky and have 2 descriptions that are equivalent and simple. It's too much.
So,
Yeah.
sorry, just one question about, so x1, x2, those are space-time coordinates on the boundary?
Yes.
Okay.
Yes.
So it's equivalent to what we have tx in the
T and X, yeah.
Okay.
Yeah. All right. Yeah. Okay. Now this geometry, this is a saddle point of Einstein gravity. Okay. And I just want to quickly comment. Typically, when we write down the bulk action in holography, in the spirit of effective theory, we want to write down sort of only the lowest order terms that we need. So only the lowest orders and derivatives and so on. The one key exception to this is this cosmological constant. Okay? And this cosmological constant has to be fine-tuned. It's related to the ADS radius. The balancing of these 2 terms is what supports anti-de Sitter space. Okay? So this is sort of the one fine-tuning that you need from the bulk perspective. Okay. So suppose that we have some scalar field in the bulk. So we have this Einstein gravity action plus ... including some scalar field phi. And suppose that it has some bulk equation of motion. This equation of motion will always be nonlinear. We might have explicit nonlinearities like this. This would come from a phi cubed term in the action. But this equation is also nonlinear because these are covariant derivatives and they couple to the metric. Okay? So this is always coupled to gravity. It's always a nonlinear theory. Okay? Near the boundary of ADS, if we assume that the region near small r in this geometry takes this form, okay, then near r equals 0, we'll be able to expand our bulk field, at least at the level of the semi-classical equations of motion. There will be essentially 2 leading terms with polynomial corrections, up to this coefficient. The purple term here, phi naught, is essentially the source. Okay? So in our holographic dictionary, we said that this generating function was dual to gravity. The source phi naught in that generating function is showing up here. Okay? It's the boundary condition on our bulk field as advertised. This other term denotes the response. Okay? So this expectation value of O, This is the expectation value of the dual operator to phi. And so if we want to calculate, for example, linear response in holography, we will wiggle this term on the boundary. We'll solve the bulk equations of motion, and then at the end, we'll read off the expectation value of O. Okay? So it's very easy to calculate things like a conductivity because we'll just essentially need to solve linear equations of motion in the bulk. Okay? And reading off correlation functions in this simple way will be something that we'll talk a little more about in the afternoon. But I just want to give you a flavor for how that works. Okay? Just to give one quick example, so ADS is a rare example of a geometry where we can compute lots of things analytically. If you calculate, let's say, the response of the bulk field to a delta function source at the boundary, you actually get this. And you can read off from this formula that the expectation value of O is 1 over x to the 2 delta. That's precisely the 2-point function of a scalar operator in CFT. Okay? So the duality is working as advertised. Okay. All right. Now, there are a number of systems in condensed matter where the scale invariance is not relativistic. Okay? So if, for example, we rescale the spatial coordinates by an amount lambda, we might rescale the time coordinate by lambda to the z. This z will be called a dynamical critical exponent, and in a number of interesting non-Fermi liquids, this is not one. Okay? Another common feature that you can have in condensed matter systems is that you have what's called hyperscaling violation. I'll just define this as the statement that at low temperatures, the entropy density S of your system does not scale as T to the d over z. T to the d over z is what you'd expect if you basically had a gas of photons with dispersion relation epsilon is k to the z. Okay? This theta denotes violations from that sort of simplistic scaling. And the classic example of hyperscaling violation would be a Fermi surface. Okay? It's telling you, loosely speaking, that your excitations effectively live in d minus theta dimensions, not in d dimensions. Okay? And in the Fermi surface, right, that's because the excitation is only mobile in the normal direction to the Fermi surface. Okay. These sorts of systems you can build holographic geometries for. I won't tell you what the bulk action is because I don't think anyone would really appreciate that. But you can write down metrics, and they're not too much more complicated than ADS. Okay? Like for the ADS metric, this metric is covariant under all of these scale transformations. Okay? So this geometry is encoding the symmetries, some of the symmetries at any rate, of our boundary theory. Yes?
Is there a string theory justification for these?
In some cases, yes. So usually you have to look at what are called consistent truncations of supergravity. Many of them do actually have IR geometries that take this form. In some sense, this is the form that you have to get in the IR unless you have a gap system. Okay. So I guess the worst thing you could do is break some additional rotational invariance in space. And there are examples of that too. You can do almost anything you want. Okay.
Is Z integer?
No.
Or it can be anything?
It can be anything. It has to be bigger than 1 for at least consistency with certain, I think, null energy condition in the bulk. But that's the only constraint that I know of.
And sorry, maybe I'm misunderstanding there, but so it says x goes to lambda x, and this somehow implies that t goes to.
Well, all I mean is suppose that I rescale all of the spatial coordinates by lambda.
Okay.
So then, if I have scale invariance, I don't get to again freely rescale time in general. The amount that time gets rescaled is fixed, and that z just tells you by what exponent it's fixed.
So this scaling and conformal invariance, this is of the bosons of the theory. Whatever was the dispersion of terminals, if we had any, was hierarchical or parabolic, it doesn't matter at this point. We're only looking at bosons.
So yeah, I would say that I don't know whether a holographic. I don't know of how to construct a holographic dual if you had a theory with multiple dynamical critical exponents. I don't think that's ever.
I just mean the single particle dispersion, if we had any. So we start the system with a parabolic spectrum or with direct spectrum, but it's not what you mean here. This is
This is, yeah, in the.
bosons which.
Yes, in the ultimate strong coupling limit, this is essentially the physics of that theory. And for example, this coefficient z shows up through the entropy, and there are other scalings that would depend on d and theta differently, and you can think about these z and theta as in some sense being thermodynamic in origin. Okay. All right. So that's about the ground state. As advertised, one of the powers of holography is that it's very good at dealing with states that are, for example, at finite temperature. There's a very nice story about finite temperature in particular. In holography, adding finite temperature means adding a black hole to the bulk. Okay? And maybe I'll skip this slide. Basically, it's one way of understanding why black holes at finite temperature by Euclidean near horizon geometry, but I'm running behind. Okay, so I would say more physically, one way you can think about these black holes as encoding finite temperature states is that the horizon has an area. In the boundary theory, this means that per unit volume, you can count how much of the horizon there is. That scales as, well, a length scale to the d. Which length scale? It's the coefficient of the metric, gxx to the d over 2. This scales as t to the d minus theta over z. If you look at one of these black hole geometries with hyperscaling violation and finite z. And that's, of course, what we said it should have been earlier. So this is at least a sanity check that what we're doing is consistent. Now, a little more seriously, back in the 70s, Bekenstein and Hawking noted that black holes appeared to have entropy. Okay? It appeared as though they could write down thermodynamic relations for a black hole, and black holes had entropy. The second law of thermodynamics was, for example, the notion that you threw things into a black hole and they fell in and they were gone forever. Okay? So area of a black hole is not decreasing, corresponds to second law of thermodynamics. And there was a particular coefficient, 1 over 4 gn, that related the two sides. Okay? And this relationship, if you're a little more careful, you precisely recover in holography. Okay? So you can calculate the entropy of your boundary theory. In some of these bottom-up descriptions, you can calculate entropy in the bulk, and these two agree. Okay? All right. So that's finite temperature. If we want to do finite density, it's pretty similar. So in the field theoretic language, let's say we take a Hamiltonian, we deform it by mu times q if we want to work in the grand canonical ensemble. In the action framework, it would look very similar. We just perturb the action by chemical potential times the charge density, or JT. So in the holographic dictionary, we know that J mu, the charge current, is dual to a gauge field in the bulk. Okay? And so we need to find a geometry where that gauge field, its time-like component at any rate, asymptotes to this chemical potential. Okay? And if we find this geometry, this is our charged holographic model. Now, let me note that this is not, you cannot gauge this away. Okay? When you have a horizon, generally AT has to vanish for this vector field to make sense. Okay? And the relative difference between 0 and mu is what encodes your finite chemical potential. If you want to add disorder, if, for example, it's charge disorder, well, you would just take this coefficient mu, you would promote it to be a spatially inhomogeneous function, and that would correspond to a spatially inhomogeneous boundary condition on AT. And this is how you study systems with disorder in holography. Okay? So the equations will be a little more complicated as they're not translation invariant, but they're still classical PDEs. Okay? This is much simpler than, for example, if you wanted to add quench disorder in field theory. It becomes quite irritating. Okay?
So,
yeah.
have these calculations been done?
Yes. That's next slide.
Is the sorry, can you go back to the previous slide? Yeah. So it says find the geometry with that condition on AT. Is there a uniqueness theorem?
Yes.
Is it unique? Okay.
Yes. These are. Yeah. I mean, as I said, this is a superficial view, but I'll show you on this slide. I mean, this is a classic solution, okay, and it's the unique solution for its specified boundary conditions. So the simplest holographic theory that would have a conserved charge, so chemical potential, as well as energy and finite temperature, this would be the following Einstein-Maxwell theory. So we have Einstein gravity, that's term 1, and then the second term is the Maxwell theory. Okay? So there's an exact nonlinear solution to these classical equations of motion that come from this action. It's called the ADS-Reisner-Nordström solution. And here it is, okay? So as a function of mu and temperature, this is the unique gravitational background. Yes?
I want to go back to the previous slide. When you're saying you cannot gauge it away, you're saying if I just try to gauge it away, then I'll have some trouble at the black hole.
Yes. So for example, notice that okay, so here r plus is the horizon coordinate. When r equals r plus, a vanishes. Okay. All right. So let me focus on a particular feature of this geometry, which is very important. If you calculate the entropy density of this system, you find that at high temperatures, it scales as temperature to the d. That's what you would expect if you had a conformal field theory at high temperature. At low temperature, you find that this entropy is constant, okay? It scales as the chemical potential to the d. So it seems as though the third law of thermodynamics has been violated. To understand what that means, let's zoom in on the low temperature part of the geometry. This is in general a very useful thing to do in holography. What we find is that we started off with a theory that looked like ADS to the d plus 2 in the UV. Okay, so when r goes to 0, this metric f is 1, and this is just the metric for ADS. In the IR, when the radius approaches the horizon, we get the following metric, which you recognize as ADS2 times r to the d. The fact that space is no longer participating in scaling tells us that we have what's called local criticality. We can say that z is infinite, okay? And this means that basically under the renormalization group, space no longer scales, okay? So you rescale time, but space is just frozen. It's as if you had a critical system at every point in space, okay? That's very similar to what you would get if you looked at, for example, the Sachdevyi-Kataev or SYK model, which is a sort of more recent realization of somewhat similar physics. In this system, you also have an extensive entropy at low temperatures. And I think through the help of systems like this, we've come to understand this is probably not well, maybe you think it's pathological, but it's not telling us that this theory doesn't exist, okay? It is very possible to find a many-body, quantum system with no quasi-particles that has an extensive entropy, and it's just coming from the fact that the energy spectrum of the many-body Hamiltonian is very finely spaced all the way down to the ground state, okay? Typically, if you had quasi-particles, you would have energy spacings that scale as 1 over the number of degrees of freedom to some power related to, the energy spectrum of low-lying excitations. In these strongly coupled soups, you have instead this exponential energy spacing, okay? All right. So in addition to this local criticality, which at least we have convinced ourselves isn't completely pathological from a theoretical viewpoint, there's another interesting feature of this system. Normally, when you look at a condensed matter model, at least in the simplest models of quantum criticality, the quantum criticality exists by fine-tuning one parameter, okay? So you might have, for example, a superfluid and an insulator, and you would tune a coupling constant to take you between those two phases, and there would be one special coupling that was a critical theory, okay? Here, the coupling constant mu is critical for all values. So we have what's called a quantum critical phase, okay? This has interesting consequences. For example, if you have, let's say, some scalar field that sits on top of this Einstein-Maxwell background, the scaling dimensions of this operator in this IR theory will be dependent on the wave number at which you look, okay? And so you get these kinds of interesting exponents that change both as a function of your tuning parameter and as a function of your wave number, okay? I don't think there's any evidence for this sort of effect in any sort of experiment, but it is a sort of peculiar and striking prediction of these simple holographic models. You can take this as a negative thing if you desire. Okay. And in general, the take-home message that I want you to have is that we can turn on things like finite density, and the emergent low-temperature physics is governed by the IR, the near-horizon part of the bulk geometry. Okay. All right. Now we can be even more exotic if we choose. So let's suppose that we have this scalar field in this charged black hole background. You'll recall, hopefully, that I wrote a formula that looks like this earlier. So if you have a scalar field phi that's dual to some operator O, okay, the mass of that operator in the bulk, the mass of the field in the bulk, corresponds to the operator dimension of the dual operator. Okay? And if you just look, this is a quadratic polynomial, and there should be a minus sign sitting in front. Sorry. Anyway, so if there were a minus sign in front, which is what it should be, you would see that this object has a minimum. Okay? And the minimum value corresponds to this. Below this value of mass, you have instabilities, you have tachyons, okay, and your theory doesn't exist. Now, it's possible in these charged black holes to have a situation where in the UV, you have a mass that's negative, but not too negative, okay? And then you turn on the chemical potential, and the mass becomes too negative for the interior geometry, okay? The resolution of this instability is superfluidity, okay? If this object is charged, which it will be for the simplest versions of this story, okay? And so holographically, we've realized that these sorts of weird gravitational instabilities are actually just avatars of the conventional instabilities that we know in condensed matter physics, okay? There's an interesting fact about these holographic superfluids, which is that they violate no-hair theorems from classical GR. And that's not an inconsistency because these are systems in ADS space, in asymptotically ADS space. Okay? And so a lot of the sort of theorems about the uniqueness of black holes rely on the lack of negative curvature. And once we lose that, we can get a whole zoo of new black holes that exist. And essentially, our ability to model lots of different phases of matter through holography is a consequence of the absence of these classical no-hair theorems for black holes. Okay? So just a fact about GR.
Could you be a little bit more specific when you're saying you make the mass on the boundary negative but not too negative?
So it's the mass in the bulk theory, right? So we write down this action, and m squared can be negative as long as it's bigger than this value in a CFT. And then we turn on a chemical potential, and this value of the mass becomes too negative in the ADS2 part of the geometry. And the resolution of this is that the field phi, this is a physical instability now, and the scalar field will condense and essentially form a charged condensate that floats above the charged black hole.
On the chemical potential, meaning that turning on the electromagnetic fluctuation involved.
Yes. And what will happen is basically that this condensate will suck some of the charge out of the black hole, analogous to charge getting condensed in a superfluid phase. Okay.
So you mentioned earlier that to put temperature in the system on the boundary means introducing black holes in the bulk.
Right.
So does it, like, introducing 1 to like 3, how many number of black holes you introduce, is that somehow?
Sorry, so what do you mean by numbers of black holes here? So there's always one black hole in all of these examples that I'm talking about. So we just have essentially a planar black hole. Think about it as just a translation invariant in the boundary spatial directions black hole. What we're asking about is basically what floats on top of this black hole and what does the geometry look like away from the horizon. That's what's changing as we, let's say, go from the normal to the superfluid phase. Okay? And as you heat the system up, there will be some critical temperature where you don't see enough of the ADS geometry in the interior to have an instability. Okay? So just like in an ordinary system, you heat it up, and the superfluidity will disappear. Okay? All right. Now, there is something nasty, if you like, about these holographic systems. So let's focus on the case of a system in 2 spatial dimensions. So little d for me will always mean spatial dimensions, not space-time. So in d equals 2, right, we would have algebraic long-range order at finite temperature. Okay? At least sufficiently low, but not 0 temperature. And in holographic models, if you do the mean field, the semi-classical gravity calculation, this is not what you find. You find that the system orders all the way to the critical temperature. This is a great example of when I said you cannot take you can't take yourself too seriously, okay? And if you take yourself too seriously, you violate the Merman-Wagner theorem, okay? The resolution to this is, well, we know it, but it's not maybe the nicest answer. It turns out that this exponent alpha in holographic models is proportional to Gn, or 1 over n squared, okay? So what this means is that well, one way of understanding this is that the superfluid condensate is 1 degree of freedom, and there's sort of n squared degrees of freedom that are hidden behind the horizon. Okay? Only the condensate is contributing to this decaying exponent, and this is why it becomes quite small. I'm not sure, how seriously you should take that cartoon, but this scaling is certainly correct. Okay? Now, there's something even more annoying about this, which is that you'll recall that Gn was our perturbative parameter. Okay? So if we want to calculate things at order Gn, this means that we're doing not loop quantum gravity in the sort of heuristic popular sense, but we're doing essentially loop corrections in our theory of quantum gravity. That's what you have to do to restore the Merman-Wagner theorem in a superfluid. Okay? So this is an example of the sort of thing you should not use holography for. All right. You can do things that are even more crazy, and there's been a bit of an industry for this, probably about 3 to 5 years ago. This is an example where there's some crazy bulk action. I don't remember what it is. It probably has like 4 or 5 fields. And you form a triangular lattice of essentially current whirlpools. Okay? This is something that you can realize, spontaneous formation of crystals and vortex lattices in holographic models. So you can get charge density waves, all sorts of other exotic phenomena if you're patient enough. Okay? All right. In the last few minutes, I want to comment on entanglement, because this is something where I think there's really a very nice connection between holography and many-body systems. So consider a many-body quantum system in some mixed state and define its entanglement or define its reduced density matrix by taking some subregion of space A and tracing out all of the other degrees of freedom. Okay? The entanglement entropy is then the von Neumann entropy of this reduced density matrix. Now for a static geometry, the entanglement entropy of a region A was conjectured by Ryu and Takiyanagi to be the minimal area of a membrane that essentially hangs in the bulk and is homologous to the region A in the boundary theory. This conjecture was proved at leading order in the gravitational coupling constant about 7 years later, and it's been even proved beyond that, I think, more recently. This is actually something that's really nice in holography, because entanglement entropy can be kind of annoying to calculate in field theories, but it's quite natural in the holographic context. For example, if we just do a simple calculation, entanglement entropy of a region of radius r, we find that there's an area law for d not equals to 1. This is the same thing as the ordinary area law in quantum systems. There's some UV sensitivity in the bulk gravitational theory that we know very well in condensed matter physics. This would just be the lattice spacing. Okay? So this is a natural regularization. In addition, and that's coming from basically the part of this membrane that's very close to the boundary. If you have a black hole, this membrane will sort of swoop towards the horizon and then hug the horizon, and you'll get some volume law contribution, which is just the thermal entropy. And that's just counting the area of the horizon. Okay? This is completely what you would expect on field theoretic grounds. If you want, you can understand entanglement growth in time-dependent phenomena. It's just like there's some natural generalization of this I won't describe, but you can calculate the dynamics of entanglement quite easily as well in holography. Okay, the last point that I'll make for today is maybe a little technical, but maybe some of you will appreciate this. One way that you can think about this ADS geometry from this information theoretic standpoint is that the bulk geometry is basically encoding the pattern of many-body entanglement in your ground state. So let's say we're looking at the zero temperature geometry and it's ADS. This is like we have a conformal field theory in the boundary. And if, for example, we're in 1D, one way that we can sort of construct a conformal theory, at least in the IR, on a many-body lattice would be, we have some individual lattice sites on the top. We apply some unitary gates to pairs. And then we essentially apply another unitary gate to neighboring pairs. This forms what's called a Mera network. The entanglement entropy between two regions of this Mera network is basically the number of bonds that you would have to cut to get from this point to this point, and that's precisely our Ryutaki-Yanagi formula. Okay? There's a conjecture that maybe one can build the bulk geometry from the pattern of entanglement that you know exists in the boundary theory. I think this is, in principle, a promising idea, but in practice, it's never been realized in I would say, a particularly successful way. But this is at least some sort of encouraging sign that this bulk theory, the bulk geometry, isn't some random artifact, but it is encoding something physical about the information content in the field theory. All right, that's all.